All right, last night in your homework, I asked you to read these pages in your packet, and basically it's a summary of things that you've already learned, things that some you learned in middle school, some you learned in Algebra 2, and some you learned in Pre-Cal. But I just want to go over and highlight what's going on and how this fits in calculus, and then how the calculus fits to physics. So we're talking about three measures. We're talking about the position of a particle or a car or something. We're talking about the velocity, and we're talking about the acceleration. Now, the position of a particle, which is usually and most often denoted in most books as S of t, indicates where a particle is, and that could be measured in feet, inches, or whatever, a linear measure. The position of a free-falling particle, which is something that you did in multiple classes, Algebra 1, Algebra 2, and Pre-Cal. This is a formula that you must know. Negative 16t squared, that has to do with the force of gravity. T, of course, is time. V sub 0, I already wrote that, good. V sub 0 is initial velocity, so times 0, and S sub 0 is initial position. Now, think back to middle school. You know from middle school that distance is equal to rate times time. So, if we solve that for rate, which is really velocity, we get rate is equal to distance divided by time. So if I wanted to know the average velocity, for example, you go to visit your grandma, it's 300 miles away, and it takes you 6 hours. You can calculate the average velocity that your car was traveling by the change in position, which would be the 300 miles, over the change in time, which would be the number of hours, and that would give you average velocity. But as you're traveling to Grandma's house, if you wanted to know exactly how fast you were traveling at the 1 hour mark, that would be your instantaneous rate of change. Now, instantaneous rate of change, we know, connotates derivative. So if we want to know how fast the car is going, we're going to take the derivative of the position function, which will give me velocity, as you can see in the box that I've highlighted here for you. You got to know that. Now we're going to do the same thing with velocity. If we want to know how fast velocity is changing, we can find the average velocity by doing the same thing. As you can see, average velocity would be change in velocity over change in time. That would be a starting and a stopping point. Over here, you can see that I've shown you where the units for acceleration come from. Just doing the same kind of unit work that you did in science, and you get feet per second squared for acceleration. Now, if we want instant acceleration, then it's instantaneous, so we have to use calculus, which implies a derivative. So as you can see from this box, the first derivative of velocity is acceleration. It measures how fast the velocity is changing. Now, if it's true that the first derivative of position is velocity, and the first derivative of velocity is acceleration, then it seems to only make sense that the second derivative, and yes, you can take a second derivative of position will be acceleration. You have to put all these ideas in your mind, and you have to memorize them. All right, so then I asked you to apply what you just learned and what you just read, and you were supposed to also read some of this from your textbook. Suppose Mr. Jernigan drops Justin, a former student, from a height of 100 feet onto a very soft ground. Determine his distance, his being Justin, from the ground at 1 second, at 1.1 seconds, at 1.5 seconds, and at 2 seconds. Now notice that this question is asking you basically for his position. Where is he in the air? So the first thing we have to do is we have to write a position function that incorporates all the given information. So Justin's position is equal to negative 16t squared plus the initial velocity. Now, since Mr. Jernigan is dropping Justin and he's not throwing him with any force, there is no initial velocity, so there will be no second term, or you could think of it as 0t. And then we're going to need to add the initial height. He's dropped from an initial height of 100 feet. And you see very quickly that this is simply some Algebra 2 work. Now, I'm not going to give the answers to all of these because you would use your calculator. You would substitute 1, and you would substitute 1.1 and 1.5 and 2. And it would tell you, for example, at 1 second, Justin is 84 feet. He is at a height of 84 feet. Okay, simple substitution. Part B. Now we're going to go into a little bit of Algebra 1. We want the average, and the key word is average. Whenever you see average, you know that it's simple slope. We want the average rate of change, so it's going to be change in position over change in time. Notice that you have a beginning time and an ending time. So the first thing I'm going to need to calculate is what is the position at 1, and from the previous problem we know at 1 second he was at 84 feet. And from your work in the first problem, at 2 seconds, he was at a position, hopefully if I copy this right, of 64 feet. So if I want to find his average velocity over that period of time, it's literally going to be change in position, so 64 minus 84 over 2 minus 1, which will give me negative 20 over 1, which is negative 20. It is a rate, feet per, I think it's second. Now, you know and I know that the negative indicates that the object, in this case the object being Justin, is falling. Whenever the velocity is negative, the particle is falling. Okay? Part C. What does his average rate of change represent? I just told you. It represents his average velocity, or his velocity over a period of time. But keep in mind that it is an average and it's over a particular interval of time. And I keep wanting to say, are there any questions? But you're not here right now, are you? Part D. Determine Justin's instantaneous. Key word. Always look for your key words. Instantaneous. That tells us calculus. So we want the instantaneous rate of change at t equal to 1 and t equal to 3. So if I want to know the instantaneous velocity, we said on the other page that I need the first derivative of position. So from above, if I take my position function and find the first derivative using the power rule, I get negative 32t, and the derivative of the constant 100, of course, is 0. And the question says, what was his instant velocity at 1 second? So I'm going to substitute 1 in here. And when I do, the derivative at 1, which again is the velocity, will be equal to negative 32 feet per second. Same thing with 3. I'm going to substitute 3 in place of t. 3 in place of t. And that will tell me his velocity in feet per second. And that is his instant velocity. If we took a picture and we froze time and we wanted to know how fast he's moving at that point, that would be the instant velocity. And then finally, we have another Algebra 2 question. At what time? So we know that they're asking us for the time when Justin hits the ground. Well, if Justin is hitting the ground, obviously his position from the ground is equal to 0. So this is a fancy way to say, when is Justin's position equal to 0? So we set negative 16t squared plus 100 equal to 0. Subtract 100 from both sides, divide both sides by negative 16, take the square root of both sides, and I'm looking for my answer, and it turns out to be t is approximately plus or minus, it could be exactly, but I'm not quite sure, 2.5 seconds. Now in this case, since we started at time 0, negative 2.5 doesn't make sense. So we know that it took 2.5 seconds for Justin to hit the ground. So he obviously did not have very long to be afraid.